This is Rutherford's Gold Foil experiment. On the right we have a vacuum pump which is connected to the chamber here, the dome chamber. Inside the chamber we have a source of alpha particles here, a gold foil here and a detector here. The detector can be moved by using the mouse scroll wheel over the wheel here. This is an electronic counter which we can start, stop and reset. Enables us to count the number of particles being detected by this detector here. This is one of the most famous experiments as it revolutionized our ideas of the atom. Before Hans Geiger and Ernest Marsden performed this experiment under the direction of Rutherford, the atom was known to be made of positively and negatively charged particles, but the structure was unknown. It was generally accepted to be like J.J. Thomson's suggestion of a plum pudding with the positive and negative charges, like the fruit in the pudding, being interspersed throughout. J.J. Thomson had discovered the electron in 1897. Ernest Rutherford's experiment of 1911 was very simple in its construction, if rather harder to perform. It consisted of a source of alpha particles aimed at a thin gold foil, exactly like we have here, but it had a screen made of zinc sulfide which scintillated when a particle hit it. That is, it created a small flash of light which could be counted by the observers. In our version of the experiment we use a detector coupled to an electronic counter which makes the experiment rather easier to perform. The alpha particle source is in a lead box with a small hole which creates a narrow beam of particles that are aimed at the thin sheet of gold foil in the centre of the apparatus. The apparatus is within an evacuated chamber to prevent the alpha particles hitting molecules in the air. What is found is that although the vast majority of particles go straight through the gold foil without changing direction, some of them are deflected at angles that are even larger than 90 degrees, which simply could not be explained by the plum pudding model. It is relatively easy to calculate the deflection that the plum pudding model might produce, and the probability of a deflection of 90 degrees or more is vanishingly small. Rutherford put it rather colourfully as, it was if you fired a 15-inch shell at a sheet of tissue paper and it came back to hit you. Rutherford deduced from the experiment that the atom had a positively charged centre that contains most of the mass of the atom. This he called the nucleus. Alpha particles are positively charged, so must be repelled by a concentration of positive charges, i.e. the proposed nucleus. As relatively few alpha particles were deflected by the gold foil, and very few indeed were bounced back, Rutherford deduced that the nucleus must be very small. We can rotate the detector like this, and if we switch the detector on, what you can see is very, very high rate detection in the central position, and as we move away from it, the rate dramatically decreases. Rutherford calculated exactly what distribution of particles would be detected by his new model of the atom, and it is this that can be verified by this experiment. What you need to do is take readings of the number of particles detected in a given amount of time, say a minute, by the detector, for angles of 0 degrees through to 10 degrees. Counting the number of hits on the detector each time, and you will need to reset the counter for each set of readings. You can then verify the results by following the method given in the documentation. Thank you.